took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster, right? That's over.
The future is parallel. Single cores are not getting any faster.
So before we talk about memory hierarchy, the second lecture on cache operations today, there is one like personal thing I want to share with you is more about like, my feeling about since the quarantine started is actually, if you want me to pick a sim song of this period of time, I would say all by myself, because most of the time I'm staying home just by myself, or given that I'm a single person. And then when I am lecturing, it's all by myself. So imagine that every time when I am doing the lecture, I have to, so here's what I'm going to show you, right? So this is what happened when I am lecturing. So you can see I have 4 different screens. So one is seeing my slide, the other is controlling my slide. One is looking at, okay, who raised their hands and who control the survey. And the other one is another screen to control the Zoom, because the Zoom software is designed terribly in a way that I need another, so I have to separate the Zoom control itself and the screen share function. Otherwise, when I do the breakout room, something bad is happening. So it turns out that I need 4 screens, 4 monitors to make the class on and going well. So sometimes you might think about that. I use group chat to ask professor questions, so I don't need to raise my hand. But some of you might feel like, why professor never replied that? Because seriously, see, this is my working environment, and I am not like, I don't know how many of you watched this animation before. I love this one because being a teacher is my dream, and sometimes I do feel like in the past I already feel like, yeah, maybe I should have this many hands and I can virtualize myself so that each student would see that I am an individual one. But like just being monitoring 4 screen, I already feel like I need 4 hands. I need 4 virtualized instances of myself, and I don't know how. I cannot imagine how much energy Koro Sensei has to put for his students, right? And if you and it's not too difficult to understand why, well, you should watch that animation. I don't want to reveal too much of the detail for you. And if you're interested about that animation, well, Hulu is the place. I feel like the reason why I'm putting this here is also because, I did an advertisement on Netflix, Disney Plus, and to be fair, I should talk about Hulu as well. Anyway. Right. So, so that's my personal thoughts, and hopefully that you understand my situation. And if I didn't respond to you on a group chat, forgive me, because I really don't have additional hands to do that. All right. So before we talk about the lecture content, first of all, big picture, most important, von Neumann architecture, processor memory. I don't think I have to mention it again and again, but there are things that you guys do not remember all the time, is that Instructions, they are from memory. So if you want to get instruction to the processor, one memory access. If the instruction needs additional access to data, one more. So generally, each instruction would incur one memory access. And if it's a data transfer instruction like load store, then it will have two memory accesses. So that's if you really don't want to memorize this big picture, at least remember this. Every instruction needs one memory access at least. And if you have data access operation, then that needs one more. So that's the volume architecture. And because every instruction needs memory access, so, and if you look at the performance between processor and memory, there is a huge gap there. It means that the processor is more than 100 times faster than the memory. So if you do not do anything to the memory, then the memory speed is essentially controlling the performance of your program. And it means that it means that all the table lookup mechanism won't work. All the algorithms that require data structure won't work, right? So it means that anything that you learn from the algorithm is useless if you cannot improve the memory performance. So that's important, and that's why for this class we talk about memory first. And so the memory technology use DRAM is really slow. So so people might ask, why don't we just use SRAM? But the reason why we don't use SRAM is just simply there's nothing saying that you can. But it's just so expensive. It's 50 times more expensive than the DRAM. And if you have some circuit background, you will know that each SRAM needs 6 times more transistors than DRAM. So that's why it is expensive. So instead of replacing the whole DRAM as SRAM, we just add a small pieces of SRAM and we code this as cache inside the processor. In addition to the processor core. So right now, most of the processor, the package itself will contain the processor core and the SRAM. And then outside of the processor, there is main memory, use DRAM. And whenever your processor needs to access data, it will consult the SRAM cache first. And this SRAM cache, we further divided into 3 different levels for a modern processor. And the reason is not from the practice that you have learned before, is that with multiple level of caches, it will improve the performance more with reasonable cost. And some of you might be questioning that, okay, why adding this small cache would help? And the answer is that because your program has locality, and the locality exists everywhere. So if you look at your code, most of the time, if you do not have a branch, you just go through the next instruction. So that's called spatial locality. And if you have data, especially people love array style data structure, then the access is sequential. So there is good spatial locality there. So in this way, when we talk about locality, you will easily imagine that a lot of tree structure or linked lists that you learned in data structure, they are terrible for spatial locality. So if all you care about is performance, don't use them. And about temporal locality, right? Application will repeat the same thing again and again, right? So we just talk about table lookup, right? So you would reference the same table again and again. You will update the same data structure again and again. That's called called temporal locality. And for code, people love loops, and I never saying that loops is a bad thing. The reason is because it helps us to explore temporal locality. So loops is great in terms of locality. So temporal locality, because you have a loop, so code has temporal locality. So and another implication here is that, okay, if you have locality, most of the time, your program is just building a very small amount of data instructions within a given window. So that's why SRAM works. And to make our SRAM easily capture this locality and reduce the amount of time to look up your data in the SRAM, the most popular cache structure right now is way-associativity cache. So the basic idea of way-associativity cache looks like this. So first of all, we organize our our cache basically use blocks of data as the basic unit of storage. So every time when you miss something from the cache, you will grab a block of data, not just one word, not just the requesting byte or the word from the lower level memory hierarchy. So in this way, because every time you are bringing consecutive elements, so you can easily capture the spatial locality, and you can use like policies like LRU to better capture temporal locality or something like that. But here's the high level concept you should keep in mind. Cache is organized by blocks, and associated with every block, there is a tag to help you identify what's the address, memory address prefix of data within a block. And the valid bit, meaning that the data here is trustworthy or not. 30-bit, meaning that the data has been modified or not. And to reduce the lookup time of our cache, to avoid going through all the blocks within a cache, we organize these blocks as sets. So you can consider a set as a hash target. So whenever you receive an address, we partition the address into 3 different parts. Block offset, which means that if the memory address that we are requesting exists in a block, which byte in the block is the data that you are requesting, or starting from which byte in a block you will find your data. And the second part you have to partition is the set index. So that's the hash index that I mentioned. So the set index indicates that if your data is in a cache, which set it will exist. So here it says 010, so it's this 010, so it's the second set, right? So you could imagine if the data exists in a cache, it should be in a number 2 set of the cache, and the remaining bits will be used as the tag, which tells you if the block, the prefix of the common part of the memory address within the block. So use the block offset. We know, well, so this is off, right? So we know that the data you are requesting starting from the 4th byte of the block, and this is the second set, the number 2 set, not the second set, actually the 3rd set, right? Because the number is 2 and we start from 0, being a computer scientist, 0, 1, 2, right? So this is the 3rd set. So this is where you may find your data. When we say may, there's a chance you won't find it. And look at the tag, right? If we use hexadecimal to represent it, 40, so this is 0, and this is 1 here. So if we see this is 10, this is what we are looking for, right? And if you look at the tag, the right-hand side is A1, so this is not what we are looking for, but the left-hand side is indeed 10. So NCED is actually the word that you are requesting. So here's hit, and you can use the mux to select this part as your output. So this is how cache works, and hopefully this would help you explain. And the most complicated part is that because we want to know the cache structure, but there are so many parameters you have to care about. And the textbook or other materials you can find online, they never give you a very good list of how to do this. So here is Hongwei's first formula, C equal to ABS. And the ABS, if so my slogan is like, a car should have ABS, and no matter you want to enable it or not, right? So here the C means the capacity, means how many data your cache can store. So when I say the capacity, it's excluding those text or belly bits. And A is the way associativity, like how many blocks are there within a set. And if it's a direct map cache, it's a cache with only one block in a set. So that's you can put one in there. And but if it's two-way associativity cache, you should put 2 as the A. And the block size means how many bytes are there in a block. And the S is number of sets we have in the cache. And because the block offset is used to identify which byte within a block can we find the data. So it's log of your B. And the number of bits in a set index is log of S. And the remaining bits will be used as the tag because they are the common prefix. All right. So then the last question we had there is the AMD Phenom 2 processor. And you see equal to ABS, you can find out that there are 512 sets within a cache, and the offset would be 6 bits because of your block size is 64 kilobyte, and the index is used to identify which set will your block exist. So if you have 512 and log 2 of 512 will be 9. And the remaining bits will be the text. So only one of those here is correct. So that's AMD Phenom 2, and that's where we end up with. So now, so before we start, there remember this is although this is like a one-man running game show, and this is the current standing. Every group is very close, and the target for this is not for grades, it's for real money, right? So at the end, I promise you, for the top performing group, I will issue $5 per person Amazon gift card. So work hard, encourage you to discuss. So today, the only thing we are going to talk about is how cache works. And if we have time, we could talk about cache optimizations, but I doubt we will have that time. But so because the last time we practiced C equal to ABS, I don't think we have a good outcome. So let's try this Intel Core i7 configuration right now for 90 seconds. So I know that you guys know C equal to ABS, and we can proceed. Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. time is up. Okay, so looks like we need a group discussion. So what I'm going to do is, what I would invite you to do is that pull up the file we have and now go into group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, we got a monopoly answer on D. So I just want to pick one group now. Okay, which group? Okay, Valor, to share what you guys thought with us. Raise your hand. I remember last week you guys already missed a chance. Don't miss the chance. Who is a subscriber of Team 3? If you don't raise your hand, the next time I will add a spy into Team 3 to, okay, finally. Okay, Jian Qiao.
Oh, yes. My answer is D, and what I thought
Your
is
group's answer.
Oh, yes.
Your group's answer is D.
Yes,
right. So okay. So the good thing about the scriber of the group is that even though that's what you think, right, you can tell people, no, that's not me. That's my group, right? So you won't feel so awkward if the answer is not wrong. There are 12 other people with you. Okay, go ahead.
I think first we should apply the formula C equals ABS, and
okay.
And we got
what's the C
S.
here?
C is the size 32 kilobytes.
Okay. Okay. And what's the A?
A is 8.
8. Okay. How about B?
B is 64 bytes.
Okay, and S is the unknown, right? So we know this is 2
Yes.
to the 6, this is 2 to the 3, right? And this is 2 to the 10, so this is 64 as the S, right?
Yes. So the D is not correct.
So if S is 64, so what you would know?
Mm. I
What
know
would you
D
know
is
from?
I know there are 64 sets
Yeah,
in the
so
cache.
then indicate which option is correct.
D.
No, so D is
Uh,
not correct, right? So what is correct with the hint S equal to 64?
yes, yes. So
Which one?
S equals
Which
64.
so
Uh,
which one is related to that?
uh,
So we know D is not correct because S is 64, but who else is correct?
I think A, B, C is all correct.
Yeah, but I mean, if S equal to 64, which one here does it relate it to?
I think the C.
So this C is block offset, right? So if it's block offset, what's that related?
Sorry, B.
B, right?
Yeah.
So, and for C, you can use log B, right? So that will be
Yes.
6, right? And for the tag is 64 minus 6 minus 6, so that will be 52, right? So if you have,
Yes.
okay, thanks. I think it's a great answer. Okay, so put your hand down. And so again, right, if every time, okay, so here's the thing. Whenever I hate to teach you like this because it's like an after-school learning center, right? But what I really want to tell you is that if you are lazy about how to solve all the cache simulation problems, or every problem that asks you about how many bits are there in a cache or how many bits are there in a cache, right? Put down C equal to ABS first, right? And you will know why am I talking about, why this formula is so important in cache operations. So C equal to ABS first, and then you will figure out there are 64 sets and how many bits are there in the offset, how many bits are there in the index, how many bits are there in the tag. So with those, if you want to know like, okay, how I have a total of 128 sets, so you know each tag is 52 bits, and you know how many blocks are there in your set, and then you can easily figure out what's the overhead, or say like how big is your tag array, how big is your other stuff, right? So so the question, so the answer here is D, not B. What, for some reason this animation is not made correctly. So the answer here is D, not B. Okay, so so now, and with this basic stuff in mind, we want to put everything together, and then we will tell you how cache operates. So this is how cache interact with the processor. So first of all, when we mentioned that whenever you have a load instruction, then the processor would send this load request to your L1 cache first, and or whoever is the first level cache. And again, the cache would partition your address into tag, index, and offset. Use the formula that we just tell you how many bits are there in the offset, how many bits are there in the index, how many bits are there in the tag. And we use the index to find out which set of blocks would contain the data that you want, and use the tag to tell if there really is a block that you are requesting, and use the block offset to figure to select the word or the D word. Like if it's load D, it means that I'm loading a data with a byte wide, right? So figure out like, okay, how many bytes and where it should start from to select. And then if I can find this block, then it will be a hit. I can directly return the data to the processor, put it in a register. And if all the operation can be done within one cycle, later on you will learn, and presumably, if you can take this class, you have a prerequisite of computer architecture. You know all the processor is pipeline and memory is one stage, right? So it means that this cache operation can be done within a stage, so there's no additional overhead if there is a hit. And if the processor cannot, if the L1 cache cannot find the requesting data, it means that, okay, it's not here. So you will have to, like, if you remember Inside Out, right? It's not in a control center. They cannot find Riley's good memory in a control center. So they have to travel, right? So first of all, they go to the area nearby their control center, for example, like the L2 cache, right? So, but before we can visit L2 cache, we have to make space for us to store to put the requesting data inside the L1 cache. Otherwise, the L1 cache cannot give it to the processor core. So we have to spare something first. So this operation is called write back. So if you have a data block that has been polluted or set dirty in your L1 cache, you have to write back it first. So write back it first, and then fetch the block that you are requesting. And when we say fetch the block that you are requesting, is issue another accessing request to the L2. And if the L2 can find it, we can return it immediately to L1. So then at that time, you only have to pay the penalty of accessing L2. However, if you cannot find it in L2, again, you have to spare space, meaning that potentially you have to write back your data, and before you can get the data from the DRAM. And most of the time, we think the data should be in the DRAM, and the DRAM should return the block now, and you just return all the block up to the prepared space in L1, L2, and finally return into the processor core. So that's what happened in a read. And whenever you are writing data, first of all, for example, if you want to write the data in RISC-V architecture, which we use in the textbook, if you are innocent about the SD command, you should definitely do your homework. And if we have a store instruction to the L1 cache, and first of all, we will set dirty because you are going to pollute a block in the L1 cache. And however, if the data is not found in L1 cache, you have to, again, find a victim block, or say spare a block in the L1 cache to store the block that you are going to modify. So you have to kick someone out first. And by kick someone out, if the one that you are going to kick out is a dirty block, meaning that it has been polluted and no one else would have the data copied there, you have to write it back. Otherwise, your change will be gone. So that's why you need to write back. So when you write back, you try to fetch the block. But if the block is also not found in L2, again, L2 need to spare a space for the requesting block. And if it's not found, write back, right? And potentially write back if the victim block is dirty, and then fetch the block, return the block. And when you get a block into your L1 cache, write and set dirty there. So that's the operation. And here, the cache structure we are talking about is an inclusive cache architecture. Is a write back, is a cache architecture using write back mechanism. You probably learned write through and exclusive somewhere in the textbook, and that's all good. But this is the most frequently used, and because we have limited amount of time in the class, so I just teach you this commonly used architecture. And in fact, most of modern processors would use this kind of architecture for their cache organization. Okay, so given that this is how cache works, let's try to simulate the cache. So if you want to simulate a cache, so that's starting from the most easy case. So saying we have a direct map cache, which means that each set has only one block. And this cache has a total 250 bytes total capacity, a very small cache, a block size of 16 bytes. So each block has 16 bytes of data, and the memory address that we are visiting is just this 5. So again, when we are having this type of question, right? C equal to ABS is the stuff that you have to come out with, right? So here, C is 256. And the S is unknown. So you C equal to ABS, you will know that we have a total of 16 sets. And with 16 sets, you know, well, there are 4 bits in the index, and there are 4 bits in the byte offset because it's the block size. And the tag is, okay, so here I didn't specify how many bits are there, but if it's a 48 bits address, it should have the remaining bits as the tag. So if I give you this address, right, then you can imagine the last two, the least significant A bits, they will be used for either index or offset, and the remaining are tags. So this is how it works, right? So this is when you receive an address, you should partition them like this. And you know there are 16 sets. So if I wanted to simulate, draw a table like this, well, if you want, and the table will contain 16 sets labeled from 0 to 16, and there are value bits, there are dirty bits. So, and assume that I'm just reading it, right? So, and this is the sequence of address that you are going to access. So list this out, right? And then, so this is the step of solving this kind of question. And some of you already see that I pull out the assignment 2 already, and there is going to be a question like this, right? So first of all, use C equal to ABS to figure out how many bits are there in each memory address. List out the memory addresses that you are going to access, and imagine or list the structure of your cache like this. And then partition the address, right? The last 4 bits, they are block offset, right? So when we are doing the cache lookup, we won't use them because they are only used to identify if the stuff is in a block where it's going to be. However, the block offset is irrelevant to if it's a hit or miss. What really determining is a hit or miss would be the tag and index. So if I am accessing the first address, right, the index tell me it's the 0 set, and currently there's nothing in the 0 set. So it's going to be a miss. And remember what we mentioned, if it's a miss, we have to get a block in a cache. So now we will have a block with tag 10, and we set the value bit to be 1 in a cache. And the data, if you remember from the previous slide, the data we have is an R space architecture symbol here, and then you will bring this in your cache. So this is what your cache content looks like right now. So now the next one, the next address is 100000100000, right? So this is the address we are requesting. So now again, the index is 0, so we go to the zeros, and the tag is 10. Hey, the tag is 10 here. So and this is asking for the 12s. So you can imagine the R is probably the word that it's requesting, but no matter what word you are requesting, at least the block is found. So this is a hit, right? So this also give you a good example how organized cache into block can exploit the spatial locality, because these two, they are really close, right? And because they are within the same block. So even though the first one is a miss, the second one will be the hit in this way. And now, the third address we are interfacing here with an index of 1. So we should go to the first set. And the first set, currently there's nothing in there. So again, this is going to be a miss, and we should get a block tag 10 with index 1 into your cache. So tag 10, value bit set 1, and this is CS203 colon space. Right, so this is the data that we are looking for right now. And then because it asks for the zeros byte, so you know T is probably the stuff that we are looking for, right? And then the next address, well, again, index 1, tag 10, index 1, tag 10. So it's a hit, right? And this is asking for the fourth, so this is asking for the A. So this is actually 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is probably this, and this is probably something like, okay. So this one is asking for a space, right? So this is what we are. This is the you know, this. So this is a hit, right? And now the next address, right, is an index 1. However, the tag is 11, so it's not the same. So it's a miss. And to serve this miss, we have to kick this out. We have to kick this out, and then put 1 here, advanced compute, right? And A is probably the word that this access is requesting. And now the next address, zeros, index 10, so it's in there, and it's requesting an R. So this is requesting zeros, and again, it's requesting an E. And this one, it's the same as this one. However, because previously it has been kicked out, right? So if you go look at the index number 1, the tag is right now 1, 1. So it's not here anymore. So it's a miss. And to serve this miss, you have to replace the block back again and kick the tag 1, 1 block out, and you will get the T again, right? And the next time, because the tag and the index matches, so it's a hit. So this is how it works, right? And if I have a two-way cache, right? Again, you C equal to ABS, you will know A sets and 4 bits in a block offset, 3 bits in the index, the remaining ones are tags. So because it's a two-way set associativity cache, so each set will contain 2 blocks like this. And each block, again, still have value bit, 30-bit tag, and data. And now for the first address, again, partition, tag, index, and offset. And the index here saying that we should go to the zeros, and the zeros now currently have nothing. So we put a block there and get a word we want, but it's essentially a miss because it's initially not in the cache. And the second one, again, because the stuff is right there, so it's a hit. Now, the third one, it goes to index 1, and currently there's nothing in index 1, so it's a miss, and let's put the block in there. And but the next time, because the block is in there, so it's a hit. Now, what's different is when we access the fifth address, the index 1, although it doesn't have, okay, so this is 100, this is 100, I should fix that. And the tag here, the tag 110 is not there. However, this time, because we have another block that is right now spared in a cache, so you don't have to kick this one out. So you simply need to put 110 in there, right? And now the next time when you access 10000, this is still here, so it's still a hit, and this is still a hit. And what's different here is that if you remember previously, this address is a miss, but right now if you go to set number 1, you do see 100 here, so it's a hit, and this one is also a hit. So that's how you from this one, you can see how two-way set associativity cache can help alleviating the conflict issue that we previously seen in the direct map cache. And these two examples should give you sufficient amount of idea how to simulate the cache operation. So right now, I am give you a challenging, which is going to be more similar to the scenario that you will deal with in real life, because some of you might still feel like, yeah, this is professor, you are lying to me. You tell me this is very relevant to the software development, but I don't feel like there's any code here. Okay, so here I give you the code. I give you the starting address of each data structure, and try to tell me if you have an AMD Phenom 2 processor, what's the data cache miss rate for this pieces of code? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the result, it looks like a normal distribution. So definitely this is a good chance that you guys should talk with your team. So right now, open the file that I sent out through the group chat and start the group discussion. All right, 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, it looks like most of you think it's C. So let's see which group will give us some insight in how you derive the answer. Whew. Baylor again? Okay, anyone in Baylor team? Who is your scriber of the day? Or for this question? Okay, seems like this team is very shy. So now open to other teams. Okay, so I have Joshua. Joshua, which team are you standing for?
Hi, I'm on team 2, the blue team.
Okay, so what do you guys think?
We felt C. We had a mixed vote, but the majority felt C. And the rationale.
Okay, but how you guys got that?
Sure. The reasoning was that so each of these 3 addresses, while they will have different tags, they'll have the same index, so they'll go to the same set. And so we felt that.
But how many set do you have?
So you have a 2-way set. So we felt that like 2/3 of those are always going to be missing because they're all going to be indexing into that same set.
Okay. So that's how you got C.
Yeah.
But is that the way how I teach you guys to address this kind of simulation question? So do you remember the step that I just walked you through? How does that? Okay, so first of all, you use C equal to ABS to got all the bits, right? And what's the next?
C equals ABS. Then you would use the address to see where it actually ends up indexing into the cache.
Okay, so what's the address that we are going to access the first?
So you're gonna A and B, right? You're gonna load those 2 first.
Okay, what's the first address of A?
So A is OX20000.
And B is that, right? So let's go with that, right? So the first is load A0. This is the address, and we know 6 bits are in the off. Well, so first of all, because it's too complicated, 6 and 9, right? So we have to translate it into binary. So this is the binary translation, 6 bits in the offset, 9 bits in the index. So we know the tag is 100 and the index is 0. And right now, hit or miss.
So initially it's going to be a miss because nothing's in the cache, right?
Okay, now the second address, what's the address?
The second address, OX30000.
Okay, partition again. What's the tag?
Tag is 11, and then the index is 0 again.
So
the tag is 3.
Well, actually, tag is 110, right?
6,
so it's 6, right? So index 0 again. Hit or miss?
So this would be a miss again because it's going to have a different tag.
Okay.
Even though we already put something at that index.
Right. So now load store C0, right? What's the address of it?
OX10000.
Okay, partition it, right? Tag is 010, so it's 2, and the index is
0 again.
Hit or miss?
It's going to be a miss because our 2 spots in this 2-way set associative were already taken up by OX4 and OX6.
Okay, but we only have 2 spots, right? So if we use LRU policy here, which one are we going to kick out?
We're going to have to kick out OX4. So the first one, the A0 that we loaded up first.
Okay, what's the next address?
So this would just loop over and over. So we would go back to loading A again.
Okay, so this is the new address. Partition it. Hit or miss?
It's going to be a miss because we evicted 4.
Okay, and to serve this miss, you have only 2 slots, right?
So
Because
we
this is
have to
associated.
we would have to evict B.
Okay, so can you imagine what's going on next?
Yeah, so someone in our group, I want to give them credit. Someone in our group actually did say this. They were just in the minority, but they were totally right. It looks like it's going to miss on everything.
Right, it's going to miss on everything, right? So, hey guys, but you did a very great walkthrough, and since some of your group mentioned that, so I will give you half credits. All right, and thanks Joshua. So, and thanks team too. You did a great job, right? And this, well, sometimes you will feel like this questions are tricky, but you know the reason why I'm designing this question because I want to make you guys wrong, so you will remember this, right? So. Here, look at this, right? You have a two-way set associativity cache. If you have 3 arrays, you want to make addition. This is a very simple code. Being a software programmer, easily you will write these pieces of a code. However, the cache performance is terrible on this processor, right? Okay, so now this question, the answer is actually E. Only 13% of you chose it after the discussion. So one thing that you should learn, majority is not always right. Majority is not always right, right? So so that's one thing that you should learn. So sometimes you might think, well, cheat in a homework, cheat in a midterm, cheat in a final would help you, but actually you should insist what you think if you think it's right, because other people might not be correct. So that's what I want you to learn as well, is that, you know, other people's opinion might be wrong. So if you think you are right, just stick with it, right? All right, so that's the AMD processor. And let's see, so you should have a good idea. Okay, for this question, I really cannot be lazy, right? So how about this one? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now look at the answer. We have 2 popular answers, but again, sometimes majority might not be right. So go ahead and discuss with your group. And before doing that, open the file that I just sent out. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, wow. See, that's the magic of discussion. So all of you, well, 93% of you think it's A. So let's have one group of you share your thoughts. Okay, team 4, Rocket Team.
Oh, I'll go. So,
Okay.
how I got A was, so it's 8-way set associative. You do C equals ABS. You get 64 entries per. You can think of them as distinct caches. So 64 entries per distinct cache. And then you can say that it's the for loop is 512. So it's going to get a block, and then it's going to go 64 elements, and then it's going to miss again, and then you do that 8 times. So 1/8 of them will be misses, and
okay, so that's a very good summary, right? But if you go through the steps carefully, first of all, right, this is still a miss, this is still the miss. This is like the previous question, right? So now let's go to this question, right? So miss or hit for this address, hit or miss?
That should be a miss.
But what's different from the last time?
It has 8-way set associative, so it won't be a conflict.
Right. So, well, you don't have to kick out anyone, right? So then even though it's a miss, but now this one is preserved, right? And as you mentioned, because each of this is an integer, so it's a 4-byte data structure, and each of the block can contain 64 bytes. So we have a total of 16 integers in there. So the next time you are going to have another miss would be at A16, right? So if you have the miss like every 16 elements per array, then that will be 6.25%. And thanks for Team 4's insight, you score 1. You scored 1. So for this question, right, the answer is A. Now, we have seen cache misses, right? So it's also important for us to figure out why we have those cache misses. And knowing this would help us knowing how to address that, right? So if you feel like, okay, the economy is the issue, right? How to address that? Tell me about that, right? Don't tell me that I just want to make blah blah great again, right? Or just don't tell me that I just want people to unite and that will address the question. No, that's not going to address the question, right? Tell me how the issue, right? Just tell me how to solve that, right? So first of all, we have to know what the root cause is. So the first of all, here are 3 main categories of root causes for cache misses. The first type is called compulsory miss, or say cold start miss. So using its name, it's not too difficult for you to imagine this type of miss would occur whenever the first time you access to a block. So for example, if this is the first time you know the content of computer architecture, what is cache, right? So that's not in your mind. So that's going to be a compulsory miss. However, right, once you have that block ever in your cache, it's not going to be a compulsory miss, but could be the rest 2 types of miss. So the second type of miss is called capacity miss. It occurs because your data structure that your application needs is just too big than your cache size. So saying that, right, if I have a data structure that I have to revisit many times, however, each time the data structure, I will go through saying that 4 megabytes of them, and my L1 cache has only 32 kilobytes. It's impossible for me to put all the 4 megabytes of data in the cache and it's still there the next time you visit it. So that's called capacity miss. And conflict miss is somewhat similar to capacity miss in a way that the next time you visit the stuff, it's not there. However, the conflict miss is different from capacity miss is that when the miss occurs again, the cache may not be full. So it's mainly due to that you have data replaced by other blocks mapping to the same set. So remember that example that we previously have in the AMD processor, right? Then in the first time you put A and B in there, and the third time when you put C, A is kicked out. So the next time you access A is not there. But at that time, your cache is not full at all. So that's called conflict miss, right? So it's mainly due to your set just have insufficient amount of blocks available to accommodate all the data that you want. So capacity miss and conflict miss, they are different. So capacity means that the data structure is just bigger than the capacity of your cache. So even though I have a fully associativity cache, means that the 4 megabyte or say the complete capacity of the cache is freely used, but you have the freedom to use all of them, it's still going to be a miss. And conflict miss is that because the set only contains insufficient amount of blocks for you to put all the data structure that you need to access in a short time, and one will kick another one out. So that's called conflict miss. So these are 3 different types of miss. So if we go to simulate the cache, right, and again, right, the first miss, right, you will figure out this is compulsory miss because it's not there, and the second one will be a hit, and this one will be a compulsory miss because this is the first time we access it, and the fifth address, again, this is a hit, and the fifth address here, because this is the first time we see this block, so this is also a compulsory miss. Now, for this one, it's a hit, this one is a hit, and for this one, right, we have seen this block before, but it's currently not in a cache. So, and the cache is not full. So this is a conflict miss, right? So this is how what it looks like. And if you simulate the two-way cache, again, right, the first one, we never seen it, compulsory miss. And the second one is a hit and compulsory miss. And this one, again, this is eliminated. So you can see if I have a two-way cache, the conflict miss is gone. So that's why people love to go multi-way caches. So now I want you to identify for this question real quick. We have a lot of cache misses we have 100% of cache misses in the AMD Phenom 2 processor. But how many of the misses here are conflict misses? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now there is a popular answer, but I just want to make sure that you guys know why it is that. So let's go to the group discussion for about 2 minutes. Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the result after discussion, about 80% of you think it's D. So I just need one group which, okay, instinct. So looks like the random selector today is really fair, right? So can I have instinct share your thoughts with us? Instincts. Anybody home? Okay, Vyom.
Yeah. I, uh, I think that it should be 93.75% because 6.25%, as we established, will be compulsory miss in any case because of the block size. And in this particular case, since we have two-way set associativity, so every time we'll be getting a miss, and all the other would will be because of the conflict. So basically 100 minus 6.25, that is your compulsory, results into 93.75% of conflict misses.
All right, so, okay, thanks for your insights. And so look at this. So if you go back and list the table, right, you will figure out that the first two, the first couple, they are compulsory misses. But starting from A1, they all exist in the cache before. So eliminating those compulsory misses, all the rest of them are conflict misses. And the same pattern will repeat when A16 occurs again, right? So that's why the answer of this question would be D, because 93% of them are conflict misses, and only 625 of them are compulsory. So if you remember the miss rate of Intel processors, they are 260. 225, right? So then what it means that is that with A-way set associativity, we can completely avoid those conflict misses in Intel processors. All right, so before you leave the classroom, one thing that I want to let you know. So first of all, a lot of you were saying about that. Yeah, I don't know that I have to write this in my homework, but thinking about that, right? You know this, right? So thinking about when you are doing a coding interview, nobody tells you that you should do this, and you know that I should do this because if I want to prepare a good coding interview, this is all what I need to know, right? Again, so if you want to prepare a good homework, clarify the question if you have doubts using Piazza. Clarify any assumption that you made for the given question. I know this. So first of all, although we have a textbook, I know some of you have issues of getting textbook. So a lot of the questions, they are from the textbook and they have very vague description. So if you don't know what's going on in the text and nobody answer you on the Piazza because you post late, just try to write down your assumptions. So we will give you as much grades as possible and explain a high-level approach overview of the solutions before you write on your answer, right? So those are a good practice in assignments, and hopefully that would help you in the future. And if you practice this enough, you will definitely naturally have a good coding interview in the future. So announcement, next week, I'm not going to have any live lectures because of my personal conflicts, but we will have Joe Emmer's talk. I will be there next Monday at 11, and we do not have a lecture next Monday to encourage you to attend Joe Emmer's talk. I will send out the Zoom link later, and the talk cannot be broadcasted on YouTube because Joe Emmer is a chief scientist in NVIDIA, and some of the stuff he mentioned may be not available to the public. So you should definitely attend that talk to know what NVIDIA is doing right now and what the latest update in the technology right now. And by the way, Joe Emmer is one of the co-inventor of simultaneous multi-threading, which is widely used. And he has a lot of experience in developing processors for Intel in the past. So definitely a must go. And next Wednesday, we will have an asynchronous session on YouTube, and we have assignment to do November the 2nd. And I will have an office hour this afternoon, but I don't have one. I won't have one next Wednesday. So if you have questions, post it through Piazza or ask the TA. Other than that, enjoy the rest of the day.